So our job in mechanics is to predict or explain motion. And so this lecture video is going to be about how we understand changes in motion. So I have a couple of pictures here that I wanted to show you. In the first picture, we have an object that is moving to the right, and the spacing between the object at each time interval is the same, and the velocity vector that we have drawn on it is the same length. This is constant velocity motion, which we've talked about. So this object is not changing its motion. The object below, the spacing between the object gets larger as we move to the third instance, and the velocity vector is getting larger. This is what we'll call accelerated motion, meaning that it changes its position at a non-constant rate. The way that we're going to understand this is from what we're going to call the momentum principle, which is the big idea for this part of the course. The momentum principle actually tells us that forces cause changes in motion. So this is the big idea for this section of the course. What we're going to do is we're going to try to define these two technical terms, momentum and forces, and how they interplay. So let's start with momentum. Momentum is defined by this vector p, and we can calculate it using this formula. Gamma, which is a scale factor, times the mass of an object times its velocity vector. Now, you might not be used to this kind of definition. You probably are used to the approximate definition of the momentum, which is the mass of an object times its velocity vector. The reason for this gamma is actually because when objects are moving very, very fast, we have to worry about relativistic effects. This gamma is a scale factor that depends on the speed of an object. So it's 1 over the square root of 1 minus v squared over the speed of light squared, which is c. In this case, c in SI units is 3 times 10 to the 8 meters per second. So when you have an object that's moving with a speed close to the speed of light, close to 3 times 10 to the 8 meters per second, you have to worry about this gamma. It turns out that for velocities, or speeds rather, that are less than about 300 kilometers per second, we approximate gamma to be 1. So for most objects, we really don't care too much about this relativistic correction. We're OK with using this definition of the momentum vector. Okay? So this is a very straightforward sort of definition of the momentum vector based on the velocity of the object and its mass. One thing that you'll note is that this is a vector idea, so that the momentum vector points in the same direction as the velocity vector. So how does this connect to forces? So let's talk a little bit about a force. So a force is probably what you think of as a push or a pull. It's kind of a simplistic definition, but really it's a way of quantizing the interaction of two objects. So how two objects interact, that quantity is what we would call a force. It requires a pair of objects. So you might think of a fan cart sitting on a track, and we can talk about the forces of that on that fan cart. If we have a fan on the back of it here, and that fan's turned on, there's a force due to the air on that cart that points to the right. Now this is the force that actually causes the motion, but there are two other forces that we might worry about. There's the force of the earth, which pulls down on the fan cart, and there's the force of the track that pushes up. Now, the sum of these forces, the sum of all of these interactions, has a special name. It's called the net force. So if we're to add up vectorially all of these forces that are acting on this system of a fan cart, we would get what we're going to call the net force, or you might even think of it as sort of the total interaction of this system with its surroundings. So if we look at this picture, you know that the fan cart moves to the right. You know it doesn't move up and down. So when you add these things up vectorially, it turns out that the track force and the force of the Earth are the same size. And so the only thing that matters is the force due to the air. So the relationship between the net force and the momentum vector is how the momentum principle actually works. It's how forces cause changes in motion. So the momentum principle is written as the change in the momentum with respect to time is equal to the net force. This is this big idea that forces cause changes in momentum, but quantified, okay, so that we can actually use it in a calculational sense. So a couple of things that we can look at for this. First off, if you have an object whose momentum does not change, like the first situation that we had up here, that implies that that object experiences no net force. It'll move with a constant velocity. Now, I've drawn these arrows in one direction. It turns out that any of these actually suggest the other. So the arrows are sort of dual-ended arrows. If some object is observed to move at constant velocity, it does not change its momentum, and the net force acting on it is 0, and so on. You can conclude from any of these that that's the case. This is often thought of as Newton's first law. Newton's second law, which you probably have seen before, F equals ma, is a form of the momentum principle where we don't worry about whether mass can change. We use this observable, this acceleration, instead. So we can rewrite this a little bit to show that this form of Newton's second law is exactly what the momentum principle tells us. So the acceleration is the change in velocity over the change in time. And we can multiply this m through. As long as the m is not changing, that's totally fine. So it's the change in m times v over the change in time, which is the change in the momentum vector over the change in time. So this is Newton's second law, or the momentum principle. They're interrelated, okay? So what we've done here is we've worked a little bit with these ideas. We've talked a little bit about the momentum principle, the forces, how those are interrelated. One of the things you might be asking is, where's the calculus in all this? I'm using these deltas to sort of describe how the momentum changes. What if it's changing continuously? So just as we did before, what we can do is we can take a limit as delta t goes to 0 of this ratio, delta p over delta t. If we do that, that's the definition of the derivative of the momentum. And that's equal to the instantaneous net force, as it turns out. So it must be that the way that we've written the momentum principle up here is that that's the average net force over the interval delta t. So we have to be a little bit careful sometimes when we're applying this to recognize that it's either the average force over the interval, or if we're working with instantaneous pieces, that we're going to have to use a little bit of calculus to understand that. So in the next video, what we're going to do is talk a little bit about how we use these ideas of the momentum principle to do some graphing.